I don't see you guys, but hopefully you see me. My name is Shunsuke. I'm a research scientist in Codec Avatars Lab in Meta. So today I'm going to talk about the foundation of 3D digital hand avatars. I wish I would be there, but my second son was born just a week ago, so I had to give a talk remotely. Okay, so let's get started. So last year, Lex Friedman released their world first VR interview with Mark Zuckerberg, using their photorealistic avatars called Codec Avatar 2.0. And Lex is located in Texas, Austin, and Mark was located in California. So they really talk over the internet using their photorealistic avatars. So in our lab, our aspiration is to enable such a social interaction indistinguishable from reality with authentic self, not your cartoony one, regardless of physical distance. And since this is a hand-like workshop, I want to motivate why hands are needed for social telepresence. Here I show you the head avatar's animation. I hope you see the audio. So although the photorealistic space definitely enhances engagement over the VC, but it doesn't capture all the social signal that the person wants to convey. So let me play the video with the upper body motion with hands.
I used to be like, yeah, 95 degrees, this is wonderful.
So the body motion, especially hand motion, significantly improve the social signals and immersiveness in telepresence. So this is why we believe photorealistic avatar for telepresence should be with hands and body. All right, so let's discuss the main topic for today's talk. So I want to lay a foundation for 3D digital hand avatars. So in other words, how to make the hand avatars they're accessible to everybody and useful. So in this talk, I argue that an avatar needs to be relightable and it properly account for the light transport. An avatar also needs to be animatable and support interaction with object and other hands. And avatars need to be also generalizable to in-the-wild data to bridge the domain gap. So let's discuss the relighting in the 3D hand avatars. So first, let me motivate why relighting actually matters. So this is an illustration of with and without relighting. As you can see on the left side, the person doesn't have a correct relighting. So the illumination on the avatar and the background is not coherent. And the right hand is proper relighting. So you can clearly tell that there's a person with relighting has a lot more coherence with the background and improves the immersiveness. So to better understand when we can say avatars are relightable, let's take a deep dive with the rendering equation. Oh, this might be a bit daunting to you, but don't worry. I'm going to walk you through one by one. So the first term is called emission term, but luckily the majority of human does not emit light, right? So we can ignore for now. And the remaining integral term is a critical component. So I'll walk you through step by step, okay? So the left-hand side denotes outgoing radiance from the point light P towards the viewer's direction omega O. And by integrating the contribution of incoming light omega I, okay? And if the light is emitted from omega I, it could be directly hit at point P, or maybe it can be bounced at other place and hit the point P, or it can go inside the skin and then scatter inside the skin to reach to the point P. And all those are scattered to reach the camera omega O. And the important observation here is no matter how complex these light transports are, always a relationship between incoming light and outgoing radiance are linear. In other words, if the light is twice brighter, the observing incoming radiance is twice brighter. If the light is half bright, the observing incoming radiance is half bright. So it's always linear, no matter how complex the intermediate light transport is. So the final color can be determined by this a linear transport vector called the transport function and the light intensity at the omega I. And if you integrate over all the light direction, you can determine the final color arriving at the camera omega O. And to build such a dense transfer function, our lab has developed a multi-view capture system called MUGSI. So MUGSI consists of 160 cameras and 450 lights. And for non-relightable codec avatars, we turn all the lights, and the MUGSI allows us to also precisely control the individual lights. I'm not sure that this is transmitted over BC, but the lights are flashing on the right side, and it's synchronized with the camera. So we can capture with a specified light pattern for each time frame. And to build a relightable avatar, we also need a tracking. So we have to precisely locate where the joints are, and then track the underlying geometry. And for that, the strong directional light is really challenging because of the casted shadow. So we interleave free lit frames and partial lit frames. So every 3 frame or 2 frame, we interleave those all lights on configuration. And for the remaining 2, we also interleave the partial lit frames to capture high dynamic range appearance change. Let me play the video here. As you can see, by tracking the geometry and the pose from this free lit frame, and we can interpolate for the in-between, we can model a relightable appearance model. And our first attempt to model high-fidelity relightable hand is to approximate this transfer function as a neural network. And this work is called Relightable Hand, and it's led by my former intern, Shun Iwase at CMU. This paper was published last year, CBPL. And hand has a very unique challenge for the avatar modeling because hand is articulated, and with this infinite combination of hand pose and light direction, it's really difficult to generalize the appearance under novel combination of light and pose. To address this, we inject the physically inspired features such as shadow as a part of the input to the network, and then build a final appearance in an end-to-end manner. As you can see, the avatar can be relit with a novel light configuration, as you can see here. And the shadow casted by the finger is correctly represented. And the one downside of such approach is it's a slow evaluation time. Because if you want to evaluate for the continuous environment, like your normal environment, then you have to evaluate this transfer function at every light direction. And in this work, we also propose to distillate into our lightweight neural network that holistically consume environment as an input. And by supervising this lightweight model with the pseudo-ground truth data produced by the aforementioned model, we can obtain real-time renderable, relightable hands. So as you can see, now you see the photorealistic 2 hands interaction with any pose, any illumination, and any viewpoint that can be rendered in real time. So this model achieved a 33 frames per second. All right, so relightable hands significantly enhance the realism of hand avatars. However, this approach is person-specific, and it does not generalize to novel identities. So next, I'll talk about how to make such a relightable photorealistic hand model universal. So in CBPL this year, my former intern Joshi and I worked together to build a much more scalable pipeline called universal relightable hands, or UHand. So from a collection of hand capture of multiple identities, we build a universal hand model that generalizes to novel poses, views, illumination, and identities. And this flyer can be quickly adapted to unseen identities from a phone scan. So now this your hand becomes your hand. I'm not sure if you get it, but it's a pun intended. Okay. So this flyer can be quickly adapted, and you can render your own hand and a novel illumination with any poses. So how can we make this the relightable training scalable? So one major bottleneck is this teacher-student distillation process, as this requires complex multi-stage training and pseudo-ground truth generation that requires non-trivial compute and storage. So we want to entirely remove this teacher-student distillation. We only want to train a single network that's trained with our light stage data and that produce a relightable hand model under any illumination. That's what we want. So to make it happen, the key idea is to make the neural network linear. So with regard to the lighting features, to follow the linearity of light transport. Okay. So what do you mean by linearity? Okay. So let's assume the light is either like the vector that contains a different contribution of different light cells. And as I mentioned earlier, in the earlier model, we basically aggregate all the light contribution one by one with a summation. If the network or the function f hold a linearity, that means if you take this integral, the summation within this like the vector, still it holds it still gives us the same value. So this is the linearity. And so here's exactly how we do. So to model this light transport function, we basically learn this neural network F that's linear with respect to the light feature. And the light feature is quickly compute with a physically based rendering without any path tracing. This is widely used for game engine and so on. And to make the network convolutional neural network linear, all we need is just simply remove the nonlinear activation and the bias from each convolution layers. This way, the input to the network and output hold their linearity as a part of intrinsic bias, inductive bias. So the one caveat is not everything is linear to the final appearance, such as the pose parameters and identity conditioning. So what we want is we want to selectively set the linearity and non-linearity. So we propose to modulate the linear network with our output of the nonlinear neural networks. So this way we can preserve the linearity with the light features, but retain the non-linearity with regard to other parameters, such as pose and identity. So this video illustrates the effectiveness of our linear model for unseen illumination when we only train with the point light capture data. So the key takeaway of this work is we can enhance the generalization of avatars by integrating physical property into the network architecture instead of loss function and other fancy stuff, and such as the linearity of light transport. Here we show more results. So we can relight everybody's hand under novel illuminations, even from a phone scan. And this paper has many more cool ideas, such as a neurophysical framework, lighting area GAN, physically based geometry refinement, and so on. For the sake of time, I have to omit, but if you want to learn more, please check out the paper. And most importantly, we have released relightable capture data, and relightable hand capture data for 4 identities. And the code of both relightable hands and your hand are released. So please check out our repository if you are interested.
Okay, thank you, Shunsuke, for the presentation. Does anyone have a question?
It's not finished yet. No.
Oh, sorry.
It's still less than halfway. Sorry.
Okay.
Okay.
You have a long pause.
All right.
So.
Yeah. I wasn't sure if people are taking the photo of QR codes, so sorry, I paused a little bit. Okay, so let's move on. Okay, so next, I want to talk about how accurate relighting can help the modeling of two hands interaction in the wild. So in this work, Re-Interhand, led by Gyonsik, my former colleague and professor at DJIST, we revisited the dataset for two-hand interactions. So we identified the key issue in the existing dataset. Complex and accurate two-hand interaction can be only obtained from either studio data or free synthetic. But both studio and synthetic data has significant domain gap from in the wild image distribution. So in this work, we propose to leverage the data-driven photorealistic relightable hands to augment two-hand interaction images. This way, we can reuse all the high-quality two-hand ground truth poses, but with diverse and photorealistic appearance in the wild to minimize the domain gap. So this is the overall pipeline. So we have done robust 2D 3D hand fitting for two-hand interaction and create a set of ground truth two-hand pose parameters. Then we synthesize photorealistic relightable hands using a relightable hand method and using the ground truth hand poses. And we created relightable hands for in total 10 identities. As you can see, now we have a photorealistic two-hand interaction with accurately registered Mano model. And we have done a version study on the effect of our data augmentation strategy against more straightforward approaches. So as you can see, if you train with inter-hand data, the performance is good for studio data, but drops substantially for in the wild data due to the domain gap. And we tried other augmentation strategy, but it didn't also help either. And our approach, by incorporating our training data, we achieved noticeable performance improvement for in the wild data. So this indicates that photorealistic relighting is not only useful for generating pretty pictures, but also for improving detection and 3D reconstruction for in the wild data by bridging the domain gap. All right, so now let's discuss how to make avatar free expressive, including hand motion for full body avatars. So in this ECCV, we present X avatar, a free expressive Gaussian avatars that support animation of body, face, and hand from monocular video shown in the left side. The reconstructed avatars can be animated with lots of person-specific details. So as you can see, the avatar can be animated with a precise hand and face control, and also body as well. Since the underlying geometry is based on the 3D Gaussian, it also retains a lot of person-specific details. The key to successful modeling in such a ill-posed setup is a choice of geometric representation. The surface mesh has been one of the most popular choice, as we can utilize statistical plier from a parametric model like simple and a geometric plier like Laplacian smoothness. However, it remains non-trivial to effectively model clothing and hair without reasonable template. And more recently, point-based representation like 3D Gaussian has been extremely popular, right, for its flexibility. However, as it's unstructured, regularizing them without losing expressiveness remains a challenge. So in this work, we present a novel mesh Gaussian hybrid representation that embeds Gaussian into the node of triangle meshes. This way, we can retain the best of both worlds. And as you can see, the input is unconstrained monocular video, and the Gaussian avatar without regularization exhibit many artifacts. You can turn on the L2 regularization, but it also has expressiveness. And our approach, based on this mesh Gaussian hybrid with a Laplacian regularization, effectively reduce artifact with sharp details. And here's our comparison. As you can see, our approach outperforms existing 3D Gaussian avatars based on the monocular video. And since this is a hand workshop, I want to kind of really highlight the improvement in the hand animation. So now with our avatar reconstructed just from a monocular video, we can drive the avatars with precise hand control, which conveys a lot more complete social signals like finger gestures. And the code is also released, so please check out our project website. Okay, now what's unique about hand is its extensive interaction with other hands and objects. So building a strong plier for interaction is critical for generation in an ill-posed setup. So to this end, we present InterhandGen. This is one of the first two-hand interaction plier based on diffusion model. And this work is led by super student Jihyun. She's a student at the KAIST and also now intern with us. One of the most popular two-hand interaction dataset is this Interhand 2.6M. And what we want is to build an unconditional generative model that allows us to sample various plausible two-hand interactions. And once we build such a plier, we can inject this into a monocular two-hand pose estimation method to boost performance. All right. So the key question is how to model the joint distribution of two hands. So let XL and XR be the pose parameters of both hands. One approach would be to train a variational autoencoder. However, we observed poor generalization quality with VAE, so we are not super happy. And more recently, a diffusion-based interaction modeling is getting popular. For example, body trained a joint diffusion model of two body pose parameters via concatenation. So we confirmed that this outperforms VAE in the case of two-hand interaction as well, but the quality of generation is still not satisfactory. And we argued that the degrees of freedom of a two-hand interaction is much higher with fingers, and more effective generation algorithm is needed for two-hand interaction. So we looked into further. So our key idea is to reparameterize the joint probability of two hands with via Bayes rule. So we decouple it with unconditional single hand generation and the conditional generation of the other hand. So the naive decomposition may not be that effective, as it still requires two separate networks, SIT1 and SITA2. And we are inspired by what's used in the classify-free guidance in diffusion models. So we unify the generator of them into a single network by treating single-hand unconditional generation as a conditional generation with zero vector. It's so-called conditional output, conditional dropout. And we empirically found that this reparameterization significantly boosts the generation quality, both quantitatively and qualitatively. And what's super nice about this is we can trivially extend it to interaction with two hand and an object by injecting there's just an additional like a object feature by simply adding them as an input to the network. So we also showed that our approach greatly outperforms existing generation method for two-hand object interaction. And most importantly, our learn prior can be plug and play for any two-hand pose regressors. So as a demonstration, we add our plier as a regularizer in the objective function during training in one of the sort approach called interwild. So we showed improvement in the accuracy of two-hand poses from a monocular image. All right, so lastly but not least, I also want to discuss how to free utilize in the wild large-scale data. So let me briefly recap what's the core problem. So as I discussed earlier, high-quality studio data provides highly disentangled control over lighting, expression, view, and identity. But it's very difficult to scale. So we cannot invite everybody into our capture system, right? On the other hand, in the wild data captures all long-tail distribution of humans, but everything is highly entangled. So the key question would be how to maximize the utility of in the wild data without explicitly handling those disentanglements. In this ECCB, one paper we present is Bridging the Gap, studio-like avatar creation from a monocular phone capture. So this work was led by our former intern, Shahrukh, and the idea is to build a diverse flyer model from large-scale in the wild face images and fine-tune it with substantially small yet high-quality studio data in the form of style transfer. So this allows us to synthesize studio-like high-quality avatars from a phone capture. For the sake of time, I'm going to omit the details, but please refer to the paper for more details. And finally, I'm super excited to talk about this work, Sapiens. So Sapiens is a human-centric vision foundational model that can be utilized for a wide range of tasks. So as a demonstration, we offer the SOTA models for fundamental 2D tasks, 2D pose, semantic segmentation, depth, and surface normal estimation. And what's remarkable in this work is its robustness. So the model is extremely robust for very challenging input. So in the past, I worked on various human reconstruction tasks from a single image like PyFu, PyFu-HD, and so on. And what annoyed me the most is the difficulty of in the wild generalization, because usually those high-quality ground truth data is very limited. And I looked into many different tricks, such as unsupervised domain transfer and higher quality synthetic data generation and so on, but the performance has never been satisfactory. So in Sapiens, we finally addressed this problem. Our key discovery is all we need is a large-scale pre-training with human-centric in-the-wild data without bells and whistles. No fancy stuff, just simply scalability of training, pre-training actually address this problem. And to be practical for human-centric tasks, we follow a couple of principles in this work. So first, we make the backbone natively high resolution. There are many existing vision backbone models, in particular based on vision transformers, but typically the maximum resolution for pre-training remains relatively low resolution, like 224. But for human-centric tasks, we care about details and its resolution. So we don't want to compromise its resolution. So unlike existing work, Sapiens is natively trained with 1K image resolution, and our model has by far the most flops with highest resolution in vision backbone models in the history. And next, we argue that the data curation plays a critical role for optimal performance. So many existing approaches use large-scale general image dataset for pre-training, such as ImageNet. However, the more data you use, the lesser chance you see each training sample with, right? So actually, we have to be really careful or critically think about what's actually in the pre-training dataset. So in this work, we look into the effect of the dataset domain, and to this end, we introduce a large-scale human-centric dataset called Human 300M. So Human 300M consists of about 300 million diverse in-the-world images of human, okay? And I think this is the most important figure in the Sapiens paper. So we compared different pre-training dataset using the identical training strategy. Other than dataset, everything is the same. So we evaluate the performance in the 4 downstream tasks, because what we care is not the performance in the pre-training, but actually the performance in the downstream tasks, right? As you can see, human-centric curated dataset with more images always leads to the better performance. And we also want to make sure that the model can be easily adapted to any downstream tasks. And to this end, for all tasks, our network architecture follows a standard vision transformer encoder with a simple convolutional decoder layers. No fancy stuff. Just a very, very simplistic network architecture. And to effectively blend the knowledge of the pre-trained model and the downstream tasks, we apply differentiable learning rate when fine-tuning the network for each downstream task. And for fine-tuning, we didn't do anything too fancy. Just for pause and segmentation, we obtained high-quality annotation in the studio data and just apply the standard augmentation like random cropping, scaling, rotation, and so on. For depth and normal, we just rely on the synthetic data based on the render people. So here I show the comparison with the SOTA depth and anything for the depth estimation task. And our approach achieves more detailed and accurate reconstruction. For surface normal, we also compare against popular normal estimation methods using a digital human domain. And interestingly, the number of scan data we use is the same as a PyFHD, about 500 scan, and it's roughly 1/8 of econ. It's just only trained with 500 data of a synthetic and is generalized to the in-the-world data. And what's crazy is like the model is only trained with a single identity. All the scan data we have is just a single person. So the image was never rendered with more than one person. However, the model generalized too well, even for the multi-identity cases, as shown on the top row. So all this knowledge comes from the large-scale pre-training, not from the fine-tuning, which is kind of crazy. And another crazy example of generalization is this. So for some reason, our model generalized to egocentric views as well. Just to be clear, our training data for the segmentation has 0 egocentric images. And for the non-egocentric images, usually left hand comes on the right? But so egocentric has like a left-hand side on the left side, but the model somehow correctly estimate so it doesn't mix up left and right hand. This is also a bit insane to me, but this is how it works. So we are committing to the open science and very looking forward to seeing how the community utilizes such a strong human-centric vision foundational model. And I believe this is also useful for like the hand method as well, hand research as well. And the demo model code are all available online, so please check it out. So let's wrap up. In this talk, we discussed how to bring photorealistic 3D digital avatars, especially hand avatars, to everybody, and how relighting, interaction, and generalization can help each other. And I believe future hand avatars should be all relightable with correct light transport modeling, and the strong interaction animation player is essential to bridge the domain gap. Also, my take on how to incorporate in-the-wild data is don't work on explicit disentanglement because it's really challenging. And instead, I argue that we should distillate the knowledge via self-supervised training and repurpose it for any downstream tasks. So I strongly believe this would be sufficient to achieve desired disentanglement and control, even if you have very limited training data for downstream tasks. All right, so lastly, I'd like to thank all my collaborators for those works. Thanks for listening.